AQUAEXCEL project. So, but now we go to another project, which has been launched under the All Atlantic collaboration, which is AquaVitae, and the speaker of today, was planned to be Fletcher Thompson who is a postdoc at the National Institute for Aquaculture Resources at the Technical University of Denmark, better known as DTU Aqua. He is a marine specialist in robotics engineering, sensor data acquisition, processing, and perception. Unfortunately, he has become ill, so he could not be here with us today, but we're very happy to have another speaker from DTU Aqua, who is Patrizio Mariani, and he is a senior researcher at the research organization, having a PhD from the University of Naples. He's currently the head of the group on observation technology. He focuses on the development of ocean technology, supporting next generation of integrated marine ecosystem assessment. He's also president of a large network called Euromarine. He's coordinator of a project called Mission Atlantic, and also has been a principal investigator in several projects. So I'll give the floor to Patrizio, and he will show the presentation of AquaVitae.
Thank you, Alexandra. I hope you can see my screen fine. Yes. And as Alexandra mentioned, this research was conducted mainly under the project AquaVitae, which is one of the 5, indeed, all Atlantic research projects, 2 of them dealing with aquaculture and 3 dealing with integrated ecosystem assessment. And as mentioned briefly by Alexandra, I'm the coordinator of one of those, which is called Mission Atlantic as well. The project I'm describing here today, it's indeed the work of my postdoc, Fletcher Thompson, who, as mentioned by Alexandra, couldn't make it today at the very last moment. And it is about the 3D image reconstructions in aquatic environment. So the industrial need for these 3D images is indeed widespread. So there is a need for underwater inspections, for example, of offshore industry and infrastructures. There is a need also for coastal management, because we can have much higher quality images for mapping, for example, coastal areas, but also for environmental monitoring to revisit specific sites and understand changes in the bottom topography, for example. And of course, there is a big interest also in aquaculture to be able to determine maybe 3-dimensional properties of the fish in order to better tune feed productions, or also type of infrastructure to be used and the processing of the fish. And of course, different technologies have been used to achieve these 3D image reconstructions. They are not only optical sensings that, of course, are very much limited by underwater visibility, which is generally quite poor, especially if you apply those in places like Denmark, as we do. Other option is the use of acoustic devices, which is a very good opportunity to expand your field of view. But of course, it's a bit more difficult to use, and generally they are dedicated for expert users. In any case, the existing solutions for these 3D images are generally quite expensive and rather specific to specific applications indeed. So we have been experimenting different solutions in the project AquaVitae. We started with stereoscopic systems, which have the drawback of being a bit difficult to handle, because there are different type of tuning that needs to be done. They are also prone to distortions of the images, and also very sensitive to the method of deployment, and not very good with vibrations and changing of the environmental conditions. We have been exploring then other options, also to overcome the limit of turbidity and backscatter in the water. we have used a camera system which was developed in another project called Utopia, and the camera system itself is called Utopia. It stands for underwater time of flight imaging acquisition system. And the method it works is basically it's a pulse laser that emit a pulse light indeed, and then it's kind of a scanning the environment at different depth or different ranges. And then the camera is tuned with the timing of the laser in order to get the images. The advantage of that is that you filter out all the backscatter, and you have an additional element that you know the distance of the object, and so you can reconstruct the dimensions in 3D. During the course of the project, we have been using this system, but then because of COVID and because of all the technology bottlenecks related to COVID and the manufacturing of some of these components, actually became difficult to access the camera again. So we have been exploring other options, kind of a stereoscopic system under steroids in a sense, because this camera system is a multi-camera system, so indeed using 8 cameras, 6 of them done for 3D underwater reconstructions. This is a system developed by Blue Atlas, which is a Danish company. And we have been working with them to understand possibilities of the use in aquaculture systems. In these examples that I show in the background, maybe it's not very visible, but it's scanning basically an underwater pier or a wall in a harbor. And you can see on the right, actually, that is also very good in reconstructing in 3D mussels formation. I forgot to put a zoom on that, but trust me, there is actually quite a high resolution of those images. So we managed to work with Utopia and exploring options with Blue Atlas, and we have been pushing also another type of solutions, which is kind of stereoscopic system, but much more compact and portable, and mainly used for gaming in those days. It's called the OAK-D Lite. And what we have been doing, we have kind of built around this camera system an enclosure that could be easily integrated in underwater robotic systems, like, for example, the one I show here, which is an ROV, remote operated vehicles, provided by the Blue Robotics in the US. And so we have basically designed an integrations or a system to integrate this stereoscopic camera for underwater applications on the ROV. It has, of course, several advantages. It's an all-in solution. It's very cost-effective. Was mentioned before that having cost-effective solution in for ocean applications or underwater applications is not always simple. In this case, we have actually optimized the casing and the integration methods to actually have a very cost-effective solution. The field of view is also quite good, with 70 degrees, more than 70 degrees on the horizontal plane and about 57 in the vertical plane. We have quite a lot dense, what is called depth points for 3D reconstructions. 300,000 of them, up to 10 meters, and allows for fast processing also on board of the companion computer on the Blue Rock 2, but also kind of allows for local storage and then further analysis and processing of the images later on. I mentioned a few times that this is a cost-effective, and that was actually very key for us in order to increase the number of users that can use this these camera systems. And the rough calculation we have here, it's about 500 euro. So the target matter is, of course, widespread, because that's the main advantage of having a stereoscopic system into a ROV. We think that the offshore industry for inspections could benefit from that, but also fishery applications, even maybe in the trawls, to directly measure the size of the fish that are getting captured in the fishing. Aquaculture, for all the reasons I mentioned before, to measure fish, and also maybe mussels lines, as we wish to do in Aquavita in the project, but also other type of use, including leisures and tourism. So in terms of results, this is actually a version 1 done with integration of another camera in the system. And we went there to inspect some of these mussels lines. Of course, the visibility conditions are not ideal, and there are waves and currents moving that, but still we were able to kind of reconstruct in 3D the mussels lines and make a model of it that allows for volume estimations of this. It's not only possible for mussels, but it's possible for other type of creatures. Here is a jellyfish example. So the technology seems to be able in this first version to actually do what we aim for. So which is basically to have these biovolume measurements in mussel farm. As I mentioned, this one is the first version. We are currently testing version 2 based on the OptiLight camera in the pool. We had plans actually to go at sea this month, but we have not been able to do so yet. But we are very close to apply it in a realistic environment. The camera seems to be able to eliminate most of the distortion that we had and actually allows for this fast processing. It is already fully integrated on the BlueRov, so it seems all the transmission of the information and the local storage is working. The next phase is really to tailor the software and the integration part for the needs of the aquaculture community. And we aim to do so in combination with some specific stakeholder in Denmark, where we will go out there and test our camera for a few experiments. The camera itself, actually, and the system itself is very portable. So we have done the integration on the ROV, but actually it can also be used as a standalone solution. It basically requires a Raspberry Pi to work with. And we aim to have this integration on a Raspberry Pi and maybe some Internet of Things type of communication to see if we can actually have them deployed and have efficient data transmission on land. So if you want further details on the technical part and the type of technology development we are doing, please contact Fletcher. He will soon recover, I'm sure, and he will be back in business probably in a couple of weeks. Thank you.